CubeSat aims at injecting 4 2U CubeSats to overcome inherent propulsion drawbacks and be able to provide shielding for prolonged radiation exposure. If we're able to get multiple CubeSats to do multiple tasks beyond LEO, like on Mars, on the Moon, for instance, we'll be able to increase functionality, and that will be improved by increasing, by adding propulsion flying to it. Introduction. CubeSats are limited again by inabilities to maneuver themselves, and again, the risk mitigation against launch vehicles and primary payloads. Currently, for instance, ILS and the Sea Launch don't offer direct launches for CubeSats. However, there are also lots of other launchers that do offer, but there are, as you expect, huge backlog which naturally exists because of the need for CubeSats to be launched. There's also another method which CubeSats actually get into orbit, which is deployment from spacecraft, ISS inclusive, and yeah, that's also an option, and there are also, which is what we tend to do. Getting to achieving interplanetary missions, they can actually be broken down into 4. Namely, the orbiters, the robotic missions, the lander missions, and the manned missions. However, LOSI in this case comes under the category of orbiter missions. Our mission is essentially broken down into 2, science mission and exploration missions, and they can be further be also broken down into different missions, specifically space physics, lunar dust measurements, ice deposits, and others. So why are lunar CubeSats needed? First of all, we want to see how we can probably create international collaboration between different institutions, innovative low-cost missions, economic space assets for industries, universities, and private organizations. And of course, since science and exploration is also part of it. CubeSats are also very, very limited by their inability to be able to use a propulsion system. That is because traditional propulsion systems don't scale down to CubeSat sizes. For instance, chemical and other propulsion systems. So CubeSats will naturally require some additional delta V to be able to get to deep space. And also high launch cost poses a problem, and then high radiation that they're going to be exposed to throughout the whole trip to Moon in this case. So our mission objectives. We hope to deploy third-party CubeSats, 4 of them, into different orbits, whose orbit ephemeris will be compatible with the nano-satellite lunar orbit insertion strategy. Also, to develop the satellite structure that ensures functional integrity of the whole CubeSats on board. I also want to mention at this point that the CubeSats are the primary payloads here. Also, we will need to perform measurements of plasma density, temperature potential around the lunar orbits, and density variation of submicron dust grains. And then finally, to encourage collaboration with international organizations, as I earlier mentioned before. Concept of operation. First, the satellites LOSI will be deployed to do transfer orbit. Once that is achieved, it's going to be detumbled and reoriented properly. After that, it begins a series of propulsion fires. And then at some point it proceeds and it gets captured into the lunar gravitational sphere. So once that is achieved and it's stable, the orbit is stable, the 4 CubeSats, which are the primary payloads, will be deployed. And yeah, there's a chance that LOSI will also act as communication relay satellites for the CubeSats that's going to carry the passenger CubeSats. Once the CubeSats are deployed, then it's going to proceed to a 100-kilometer circular orbit where the scientific secondary payloads are going to be performed, measurement of the lunar dust and plasma measurements, and some other ones. And I'll also mention at this point that some of the scientific instruments are going to be made at Kyushu Institute of Technology in-house unit there. Key performance parameters. First of all, is to successfully deploy 4 2U CubeSats into a requested orbit with a position accuracy of about 10 meters. Also, the measurement of solar winds and magnetospheric plasma, the measurement of submicron dust grains, and adaptive exposure capacity to analyze lunar exosphere and surface composition. I'll quickly go through the bus systems that the team has actually worked on. First is the propulsion system. The next is the AOCS. power system, communication, payload, main structure itself, and of course, the command data and handling. That's the card drawing for LOSI, represented here with the CubeSat pockets open, ready for deployment. Using SPENVINIS, radiation analysis for CubeSat was analyzed, and it was reached that 1 centimeter thickness made of aluminum alloy will be able to provide the required shielding for against radiation effect, against radiation exposure. And the dry mass of LOSI is expected to be about 43 kilograms. So after deployment, the next is going to be the secondary missions, which is essentially measurement, scientific instrument measurements. First, the CubeSat operation and lunar approach, which is essentially broken down to be an exploration mission in this case, and then the scientific measurements fall into the categories of exploration and science together. They're both explorational and scientific purpose. Orbit transfers. The initial LOSI will be initially injected into a geotransfer orbit, 7,000 kilometers perigee and 42,000 kilometers apogee. Once deployed and stable, the next task will be to escape the Van Allen belt by raising the altitude by a series of propulsion system bonds to an altitude that's greater than 60,000 kilometers, and we hope that this is going to be achieved within the first 21 days out of a total 350 days available for the complete perigee augmentation bonds. The total time of travel is estimated to be 552. In subsequent slides, we'll be able to give details of how these numbers were reached. The whole thrust bonds have been broken down into 4. The first being the thrust firing at perigee. This is essentially to raise the apogee high enough. That will be followed by another thrust bond again at apogee. But this time, the idea behind this bond is to ensure that LOSI is captured into the lunar gravitational sphere. And that's expected to happen about 310,000 kilometers away from Earth and about 90,000 kilometers away from the moon. The third bond is a thruster bond that stabilizes the orbit once in the gravitational sphere of the moon, and then finally there will be secularization and subsequent remove of energy from the orbit to reduce the altitude to about 100 kilometers altitude, where the secondary payload operations will commence. To my right, again, is at the charts or graphs that was done on analysis to actually show the feasibility of this idea. Again, that's also here, and then the next slide here shows us a summary of what we do expect, the delta V requirements, and the time required to actually reach these orbits. As you can see, the total delta V requirement is about 4.6 kilometers per second, and the total travel time is 552 days. The propulsion system, now, after the orbital analysis, it was decided that about 4.6 kilometers per second of delta V is required to actually achieve. So the propulsion system will have to find a means of providing this delta V. The weight mass for LOSI is expected to be about 50 kilograms, and a constant thrust of 0.04 newtons was chosen after some analysis. Three thrusters were analyzed through three ion thrusters, the 1 cm one, the 3 cm, and the 7 cm. All were provided by BUSEC, and we analyzed them against satellite mass against the travel time. At the end, 7 centimeters RF ion thruster was chosen because it allows us for less time to travel with So the available thrust power for the bit 7 is about 360 watts, although we do not hope to operate this at this limit because of the power constraints that we have. The ISP about 3,500 up to 3,500, and the maximum thrust available is 0.011 newtons. Although again, we do not hope to operate this at this level. So if we go back and compare a little bit, we're going to see that the thrust chosen is about 0.004. The idea is actually to cut down the propellant mass as required to take us to the moon. And the ratio of the wet to dry mass is about 1.07. Again, we were mentioning here that the propellant of choice is iodine, which was chosen against xenon because of the issues of being able to save it, and the tanks required for xenon. So it's quite a more compact choice at this stage.
Now I will continue to explain about the electrical power system. As you can see in these figures, it consists basically of the proportional panels. In the arrows show the strategy of how these panels is going to be deployed. In the top view, and in red lines, it is highlighted the solar cell effective area. And in the other sides of the satellite, we place solar cells to ensure solar energy collection while the satellite is carrying out critical maneuvers. Okay, and we are considering the use of two sets of 9 lithium batteries. These two sets are connected in parallel, making 30 amperes hours capacity. And we are planning to use high efficiency triple junction solar cells mounted and in body and deployable solar panels. According to this power analysis, considering critical modes such as transfer orbit mode, CubeSat release mode, and secondary emission, we are considering, we calculated the effective solar panel area should be 16,000 centimeters square. Regarding attitude and orbit control system, we are considering the use of 5 sensors, 1 strap tracker, 1 fiber optic gyro, 4 reaction wheels placed in tetrahedral configuration, and also 8 pulse plasma thrusters for attitude control, and also to desaturate reaction wheels, or at least to keep the reaction wheels working in the nominal value. We are considering 2 main control modes, the tumbling one. So as you can see in this figure, the strategy for the tumbling the satellite will be carried out within 1,000 seconds, and the reaction wheels will not be saturated. For the next strategy, inertial pointing, we are considering a maneuver within 1 minute to achieve the desired attitude. Again, in the other figure, showing the left, we are showing the behavior of the reaction wheels while the satellite is performing attitude maneuvers. For the communication subsystem, we are considering the use of commercial off-the-shelf transponder, which is the Iris V2 CubeSat deep space transponder developed by NASA and the Jet Propulsion Laboratory. This transponder had the feature to work within the X-band frequencies operable with NASA deep space network, but also it is capable to operate with another bands such as Q-band and S-band. For the antennas, we are considering the one-touch array medium gain antenna, which requires pointing, as you can see in this figure, and also we are considering the placement in the opposite side of this antenna, 2 low-gain omnidirectional antennas, which operate in UHF and VHF. In the table, you can see about the uplink and downlink frequency, as well as the variable downlink data rate. And last but not least, we are going to mention design considerations for command and data handling and thermal module, because somehow we are a small team and we couldn't have enough time to work on it. We just have general considerations of the system. So for example, for the command and data handling, we are considering the use of a Maxwell single board SCS 750 radiation hardened and also flight proven, and the main feature it is a threat response processing architecture to increase the error-free processing. Also, the advantage of this board, it has several serial communications based on low voltage differential signal to ensure the proper communication or proper behavior of the interface within subsystems. Also, for the thermal module, we are considering the use of active thermal control to ensure strict temperature compliance. Also, external surface and protruding components will be covered by multi-layer insulator blankets. And of course, considering proper placement of each subsystem within the CubeSat body. For the implementation plan, we are considering that QTech will lead the development of the project. in terms of design, development, and testing. Once this project is beginning, it will be launched a call for lunar mission based on 2 unique CubeSats. So there will be 4 places, so interested participants can apply and participate in this project. And also we are considering that a prospective organization should possess a ground station network to provide proper communications and orbit determination capabilities. For the LOSI project budget, we are considering the development of a flight model, which is around $5 million. The details of the cost of each subsystem, it is shown in this table, where you can see the 2 more expensive subsystems are the propulsion one and the power subsystem. We are considering also the development of an engineering model. Launch cost, we are considering this satellite would launch as a piggyback, so the cost will decrease dramatically. And as my colleague mentioned, we are planning to be launched into GTO orbit. So for the project management, integration and test, we are considering also some cost, $2 million, and it shows in total $15 million with a plus 25% margin error. But the advantage of this project is we are to mitigate some cost for the development of this project. We are considering some financial retrieval from the organizations will participate in this project by the rent space for this satellite. So we are proposing $200,000, but maybe it can be increased or in such a way that we can provide relay communications. But we are not increasing this cost because we want to make it affordable for organizations who want to participate in this project, and particularly for a deep space mission. And last, the main risk we are considering 2 programmatic ones. So first is the availability of launchers, because we are considering to be launched as a piggyback. So this is the main risk, to find a proper launcher to also apply to be launched as a piggyback, also in GTO. But the size of the propellant tanks and the power system are designed in such a way that this satellite can be placed in LEO orbit, and from LEO orbit can start the orbit maneuvers to the moon. And also we are considering some of the main risks is the availability of DNS. It depends on the organization, of course, who possess this proper deep space network. And technical issues such as communication limitations for orbit determination, AOCS loss of precision and orbit maneuver limitations, and some external disturbances such as loss of solar panels due to debris or expected perturbation can happen. So it is something that by design we can mitigate, and the prospective organization who support this project had to be aware of this main risk. So on behalf of these international LOSI team members, I appreciate you to hear us, and thank you so much.
Questions? I see that you use 8 pulse plasma thrusters to manage momentum on your wheels. Why don't you use the pulse plasma thrusters to detumble? Because now you first accumulate momentum on the wheels, and then you have to get rid of the momentum using the pulse plasma thrusters.
Yes, for the tumble itself, most of the work most of the maneuvers should be done by the reaction wheels, but maybe the perturbance is going to be so large that maybe the use of EPTs it is possible to be used, and also to keep the operation of reaction wheels in a nominal value. So that's why we are considering as a possibility to use reaction wheels and EPT thruster.
Just the last question, I see when you do attitude maneuvers, You start off from 0 wheel speeds on your 4 tetrahedral configuration wheels, and you land it up at some offset wheel speeds. Why do you use that distribution of speeds on the 4 wheels? Why don't you go back to 0 speed after the maneuver? Because that's surely the lowest energy. Otherwise, you have to maintain speeds on the wheels after the maneuver.
Okay, yes, I understand. For this analysis, we considering the initial conditions, such as 0 RPMs for the reaction wheels, but yes, but also taking into account that the speed of the reaction wheels.
I'm talking about when you do an attitude maneuver, not detumbling. This is detumbling.
Okay.
When you're doing attitude maneuver, you start off with 0 wheel speeds just to bring the attitude back to 0 attitude. Quaternion elements 0001.
Okay.
So the wheel speeds afterwards is got an offset, 2000 or 1500 RPM on
Yes.
2 of the wheels. You could have done the maneuver with the wheel speeds again at 0 speed after the maneuver, because you just do momentum exchange to rotate the satellite. There's no need that your wheels now will have an offset speed. You should use the right control law to distribute momentum on the wheels when you do the maneuver.
Yes, well, as an initial analysis, well, we showed that it is feasible to perform attitude maneuvers in that way. But yeah, you're right. I mean, maybe in the future we have to consider continuous attitude control maneuvers in such a way that to demonstrate the feasibility to perform several attitude maneuvers and without the saturated direction. Yeah, but it is something we should consider. Yeah, I think.
Yes, in addition to that, the PPT thrusters are also there to help momentum dumping for.
Actually, I want to continue on the ADC for a millisecond. You have a single star tracker, which is kind of a single point failure, so you may want to think about that one. On such an expensive mission, you may want one. The other thing is, I think that depending on the length of your mission, you should trade reaction wheels and PPTs for dumping, and just PPTs, and use thruster control. With high speed thrusters, that's an option sometimes, so it may be an interesting trade. One quick question: why 2 U's, 2 U cubes?
Actually, we thought that using 1 U CubeSat might not provide a lot of functionality, so extending it to 2 U CubeSat might extend functionality, and yeah, it's essentially
The tendency seems to be that you either do a 1 U or you do a 3 U.
Yeah.
Except QB50, which I have the same question for them. But that's something to consider. And then the final thing is that I think you need to look at your prices. The launch price, I mean, 400K is a little bit more than 3 U CubeSat. So if you have a way of getting a piggyback at that price, then that's great. But you may be underestimating the launch cost. Also, if you charge somebody $200,000 to send them to the moon, you're going to have 1 million customers, because that's really, really, really inexpensive. It's about the same price as going to Leo. So just look into that.
Yeah.
One last question.
So how can you make orbit determination after going away from the Earth?
Okay. We performed some research regarding orbit determination, and we found out that the most precise way to determine the orbit of the satellite will be by using X-band communications. With a proper deep space network, in ground, there will be calculated the signal once it reaches to the ground, and also by considering something, for example, Doppler effect. By considering Doppler effect, basically, and the ground station will calculate the orbit ephemeris, and once it is calculated, it will be sent to the satellite, and on board will be propagated the orbit. It has to be done periodically because in certain time the losses precision because of the orbit propagator can be increased in several days. So we recommend that maybe within 1 day or 2 days the ground station network should send the orbit ephemeris to the satellite.
Okay, thank you. We are going. Thank you very much. Let's thank the